is what we call channel state information, right? So what change the signal on its way to the receiver. And then of course you have the noise as on any communication channel, which you have to deal with. But again, you can train machine learning models to learn how, let's say, these Wi-Fi signals are changed. So here one example from the lab. So this is one of our students came into the lab. You see on the right-hand side of this video, you see the receiver. He's looking towards the receiver now. The EP is on the tripod behind him. You see, when he was not in the room, the CSI data was very stable. He came in, then the CSI data was, again, perceiving that was changing. He goes out again, and then this stabilizes. So you can, again, train machine learning models to learn those changes. Okay. So then we have the same categories we had before for the high performance applications. We have it here, right, for the train automation. We also have it here. So input data and machine learning techniques. So now we have much this data. So these CSI matrices are, again, of very few kilobytes per second to produce, very few kilobytes per second, and hence you can start using microcontrollers for output. So you don't need to have, let's say, a high-end model to distinguish these changes in the sequence, right? Because data is also very limited. So normally you will perform some principal component analysis that is shown on the picture below, and then try to reduce the dimensionality of this set of signals, right? And try to use the least possible number of dimensions such that, say, you can come up with lightweight machine learning models like you see here, or techniques that you see here, that for example support vector machines, and train them to distinguish different cases in this CSI. Then you have, again, a transfer gap, and then it's very much related to the nature of the Wi-Fi signals. They are affected by any change in the environment, right? So all possible changes, for example, the color of water, or that you move your chair, or again, all those small changes will also cause a variation in the signals, and hence you will have to measure a lot of data, to collect a lot of data to train these models properly. That is very time consuming, right? And it's not efficient in the long term, right? So if you train a machine, let's say a Wi-Fi sensing model for this room, it will not work probably in another room. That's the problem here. And probably you will also have differences between days, right? Because also humidity and temperature will affect your measurements, right? That's an issue. One of the other issues we're facing is that in contrast to pictures, right, where you can rotate the picture, scale them up, scale them down, cut them in some way, such that out of one picture you produce many pictures, right? You augment data. This is not done for this kind of data, CSI. We don't know how to extend it, right? So the only thing we can do is add noise, but that is very limited in the results, right? It will not really improve the machine learning models so much. Okay. Then we have also the issue of power supply and thermal integrity. So you see here, instead of being the model, the machine learning model that takes the most power, it's just the radio chip, right? Which is consuming the most power. But this can be solved like with duty cycling, right? So you switch on the radio chip, send some messages, then switch it off, and then again switch it on sometime later, and then send some messages on. So you don't send all the time like currently APs are doing, these access points are doing. So of course we have to agree on, or say, accept a trade-off with temporary resolution. So when the radio chip is off, you will not see anything on the room, right? So only when the chip is on, but you will again reduce the number of, the amount of energy that you're using, right? But in this kind of applications where we want to, for example, detect the number of persons in this room, right, which is one of the common applications for Wi-Fi sensing. Instead of just having a camera to count or sensors at the doors to count people, we just want to use this Wi-Fi sensing to estimate the number of persons here. This is one of the applications. In that case, you don't need to have the radio on all the time, right? So we can now leave the room. The number of persons will not change that fast, right? So you can switch off the radio for, let's say, 1 minute, and nothing will affect the application itself. So it's a viable solution. Then when it comes to the security aspect and the privacy aspect, we have this particular situation where the Wi-Fi sensing technology is very interesting because I don't have images, right? I don't have a camera pointing at you, right? So you don't feel observed. No one is going to see your face. But it's an invisible surveillance, right? So I can, if I train the AI, I can know exactly what you're doing all the time, right? And that is kind of a strange situation, right? There can be abuse and misuse of this technology. So you might even not notice that somebody is using your AP, your router, to kind of monitor your activities, right? That is an issue. But then you see that security becomes a subset of privacy in this particular context, which is a strange paradox, if you wish, a strange constellation. All right. So this is one of the applications where we've been, let's say, running different projects. This is one of them. It's called Wise for Car, actually. And the idea was to, again, take multiple vehicles and, let's say, install different sensors. Those sensors are Raspberry Pi in this particular setting. So you see on the dashboard you have the AP, the access point router, and we also use a camera for documentation purposes. Then the rest, you see the Raspberry Pi is distributed in that way throughout inside the vehicle. This is the way how it looks in the hardware. So you see this picture of the door. And then we collected data from many different participants, right? Many different test persons. And we then trained a model in the following way. So we just wanted to measure, or to say estimate the average weight of a person. So you see the difference. So the blue bar is the actual weight, and the red bar is the weight that our model detected out of this, right? So you see we're somehow close always. However, wherever we have like extreme cases where we didn't have so many test persons, right? Like for example, people, let's say heavier than 110 kilograms. We didn't have so many of them. Then our model was less accurate in that particular case because we have less data, right? So you have this data dependency. You will feed it in the applications you perform, right? Then we did the same for height. So the idea was to estimate the weights and the height of the driver in order to, for example, in the future, configure the airbags, right? So airbags are currently configured for, let's say, standard people, but if you are too heavy or too light, you will have not the ideal situation or the ideal protection by the airbags, right? So the idea will be in the future we can use technologies like this, which are very cost effective, right? So you don't need much for this to easily, again, perform these applications. Here again, you have the same situation. So people taller than 2 meters, right? We didn't have so many, so we didn't have so much data there. The same applies for people, let's say, smaller than 1.50 meters. We didn't have so many of them in the test, right? Most of them were in the middle of this distribution, and hence there you have the highest accuracy, or we observe normally the highest accuracy. When you have the data, you perform well, right? Okay, so I think I'm just reaching my time limit, if I'm not exceeded it. So I'd like to sum up what I just discussed. So we have this performance spectrum, right? So it's different applications will lead to different requirements, and different requirements again have originated these many different platforms that are available nowadays for purchase. And then at the extremes, we have this high-end, or let's say high-performance machine learning applications, and we saw this particular application of the railway automation. Again, overall, we can sum up all these steps saying, okay, you can let's say, process bigger amounts of data and hence run more complex models, but you don't have the issue with data representativeness and adversarial attacks. Those are still unsolved. Then you have the issue. Oh, sorry, that was not intended. So then you have, let's say, the low performance machine learning application like the Wi-Fi sensing, where you can use, let's say, microcontrollers. And again, you still have the data representativeness as an issue. And now, in this particular case, let's say this misuse abuse that has led to the paradox of security being a subset of privacy. Okay, with that, I'd like to thank you for your attention. If you have any questions. So, how do you?
Requesting the participants if you have any questions for the speaker. Yes, sir.
Coming to the first application, on the railway. So when railway is moving, how your Wi-Fi is connecting to the cloud? Because especially in railway track, we don't get a good Wi-Fi connectivity. Ultimately, we should share that information to the cloud, and only the next station people will identify that some obstacle is there or something is there. So I will share that information. So without having a proper Wi-Fi connectivity.
And we're not using Wi-Fi then. We're using 6G sorry, 5G communication. 5G communication. So it's a mobile data communication where you can reserve bandwidth. Yeah. And of course, the test field that we have is very stable. Right? But of course, the question is what is the coverage you have? Now, in train stations, you can assume it's pretty stable coverage, right? And if not, then the driver will have to drive, right? That's the idea. But if you can reduce some amount of the workload that the drivers have, that is okay with us, right? So that's enough. That's enough. That's okay. That's already advantageous, so to speak, right? But ideally, we'll always have a stable communication.
So in second, Wi-Fi sensing.
Yeah.
So if you have some kind of here some fire accident, something has happened. If the Wi-Fi is not working, so the other will sense.
Not working in what regard? No connection?
Yeah, maybe useful for any fire accidents, Wi-Fi sensing.
So if you don't have the password, let's say, of the Wi-Fi, that's so you don't need communication. You need to connect to Wi-Fi. You don't just need to get the beacons, right? So the routers, the 80 cent beacons, normally 10 every second, right? And that is enough to perform some kind of a monitoring or surveillance of the environment, right? So you don't need to connect and have access to the internet. It's just this beacon that is being sent, and that rarely is broken, right? So what normally the problems you have with the internet connection, that's a different story. But you just need this to be sending packets, right? It doesn't matter what's inside.
So here we are not training with respect to the images, we are training with respect to features extraction. What kind of features we are extracting to do all these things? Some kind of features we need to extract. So what exactly we are extracting?
Well, I mean, there are, so you see these signals, look like pretty much like that. As let me see what I find that. The picture, right, the real picture. So you see, they look very much like that, right? So the Wi-Fi channel has, depending on what, which bandwidth you are, right? So we have been using it in the 2.4 bandwidth, right? So frequency, and then you have their 20 megahertz channels. Every channel has 64 subcarriers. Out of them, some are nullified for the protocol's sake, right? So it's necessary for, let's say, knowing where to send, you nullify some of them. And then the remaining 52 subcarriers contain this CSI data. And that CSI data, let's say for each of those 52 subcarriers, you have an amplitude and a phase, right, of the data, right? That is the difference between what you send and what you receive, right? So the features you can detect in there are, let's say, transitions, right? And then the absolute values. That's it. That's what this machine learning algorithms learn, right? How these values change over time. That's it. It's not a radar. I use the example of a radar as sort of an analogy, but it's not working like a Doppler effect or something, right? It's not exactly a radar.
Thank you, sir. Thank you.
You're welcome.
Thank you, sir. With this, we'll conclude the first keynote session. So thank you once again, sir, for your beautiful insights on how AI can be integrated within better devices. Thank you, sir. So moving on to our next session, let me take the privilege to invite Professor P. Satish Kumar, IIT Roorkee, India, to deliver his speech on harnessing machine learning for Android hardware development. Over to you, sir.
Without any late, let's start. maybe good afternoon everyone. I'll try to cut short the talk and try to be brief in such a way that you get the summary of the talk. Okay. So we'll try to close maybe in 20-25 minutes. We are not too hungry. All right. Yeah. So this talk is on how to detect Android malware using machine learning techniques. So this is some research what we have done in our laboratory a couple of years ago. It's not really recent, but it gives you a basic idea how to start your research in this domain and how to move ahead in the future.
हम लोग लंच करके आते हैं, मधु सर को बोल देते हैं सर लाइव चल रहा है, हम जाके लंच करके आ रहे हैं। चल सकते हैं, इसका एक दो फोटो खींच देते हैं, सेव कर देते हैं, फिर चलेंगे।
बैठने स्क्रीन नहीं दिख रहा। चार्ज
बैटरी मांगा, चेंज नहीं किया था हमने।
Alright, so
उसमें है
typically there are several techniques to detect the Android malware. They are broadly classified into three types: static, dynamic, and hybrid kind of detections. And I'll try to give a broad picture how the detection can be done in each category, so that you can take up research in that particular domain as per your interest. So a quick brief on statistics first. These days, people are turning their usage from typical desktop-based work to mobile-based work, and the numbers are clearly indicating that your transition is very quick. Okay, and the reasons for doing that is several applications, particularly the internet browsing is very easy and quick and on the time required. Okay, so that's why it has become very popular, and of course online shopping, gaming, and there are several other reasons like particularly social media, social networking are typical examples that are the reasons why the mobiles have become so popular. Okay, and you can also see the statistics that total world population is 8.3 billion, and out of that, unique mobile phone users are almost like 70% of the population so far, and smartphone users are 65% of the total users. And if you see just the mobile connections on the whole, including IoT and other sort of devices, it has already crossed. Okay. So the number of devices what we are using every day, the basis are really increasing in large number. Okay. So this is another graph which shows why Android is also popular. Like you see, there are different operating systems that are being used in your mobile phones or smartphones in general. Why I'm using the word smartphone or smart device? Because even IoT devices are coming, even your smart TV, for example, is Android TV now. Okay. So your smartwatch is Android watch. So many devices are becoming like daily based devices, and there are
Camera side से
Android
है.
integrated by some things. Okay. So the
Camera
Android
side
curve
से है,
is
camera
also like drastically increasing, and you notice that almost 70-75% of the users are Android based users, and iOS is of course consistently doing it, but not crossing any time 20-25% of users. There were many operating systems coming up, and they are going away. So there's no much contribution here. So obviously, like